Hello again. So we're doing 10.3 day 2 today. So we're kind of focusing more in on these regular polygons like we did yesterday. But today we're going to really focus in on using special right triangles to find the areas of regular polygons. So again, you might want to have a little bit of review of special right triangles and just make sure that you are kind of solid on those so that you're not like wondering what the heck is going on today. We talked about special right triangles in chapter 8. So you might want to go back and just kind of peek at chapter 8 to get a little refresher, or look at some of the videos I posted last week, and I'll try to link them below for Khan Academy as well. Okay, so if we were in class, normally I would have you guys do this as a do now. I'd probably have you guys take a couple of minutes to read through the questions and then write down some ideas and then check with a neighbor. Obviously, we don't have that. So if you're watching this like from afar with one of your classmates, maybe you can text or team message or email them about these questions. But for now, I would just pause the video and take a minute to think through. Question 1 says, what type of a triangle is formed by the radius, the apothem, and the side of the regular hexagon? So I wrote here that a hint is to find the angles, but I would even suggest go through and sketch in a radius and an apothem. And then the second question is, how could we find the length of the apothem? So I'm going to give you guys kind of a hypothetical side length here of 10 inches. If you haven't already, I would go ahead and pause the video and sketch this out and just kind of activate some learning in your brain. So if I go through and sketch in my radius there, or sorry, this is my apothem right here, isn't it? Going from the center to the middle of the opposite side. My radius goes from the center to the vertex. So here's my radius right here. So center to vertex. And obviously we already have all 6 of our sides drawn in here. But so take a minute to think about how we kind of break down these triangles, right? So I'm badly sketching in all of my radii here. Remember we talked about yesterday, if we kind of go around this circle in here, we have 360 degrees, right? And if we take 360 and split it up into 6 parts, we're obviously going to get all these kind of 60-degree angles going on in here. Okay, so each kind of like triangular segment of, or section, I guess, of the hexagon is 60 degrees, right? 60, 60, 60, 60. Well, so now that I have this apothem here, it's actually taking that 60-degree angle and just cutting it in half, right? So suddenly I'm actually going to have a 30-degree angle up here. And if I have a 30-degree angle up at the top of the triangle with a 90-degree angle here, 30, 60 is going to be my other angle over there, right? 30, 60, and 90. So that's actually a special right triangle, right? Our 30, 60, 90 triangle. Okay, and that's going to be really important for today because we actually, in a lot of these regular hexagons, have a ton of special right triangles popping up. So when the second question says, how can we find the length of the apothem? Well, we have this 10-inch length over here already. So that was not a straight line. So what if I take that 10-inch length and say, okay, well, I know that my apothem is kind of like cutting that side length in half, right? So my apothem right here should be exactly cutting that side length in half. If the whole thing is 10, that means I actually have kind of a length of 5 and 5 that it's being split up into. Well, remember with our 30, 60, 90, to get to the radius, we double the short leg. So our radius would be 10. And then to get to the long leg, we multiply the short leg by the square root of 3. So my long leg here is going to be 5 square root of 3, but my long leg is the apothem, right? So if I know my short leg here, or even if I knew my radius and I could find the short leg, then I can just take the short leg and throw a square root of 3 on there, and voila, suddenly we have our apothem, right? So kind of the whole idea of today is we're using special right triangles to find missing pieces that we have, right? Do we need the apothem? How can we find it? Or do we need the perimeter? How can we find it? And once we have that, right, now that I know the apothem here, and obviously if I know a side length of 10 inches, I can just multiply it by 6 to get the perimeter. And then I can go to my 1/2 apothem perimeter formula and easy peasy, right, plug it in and find the area of this hexagon, kind of the big idea of today. So here's example 1. It says, what's the area of this equilateral triangle? So remember, equilateral means all the sides are the same. So that means we're going to have all equal sides. We're going to have 60 degrees and all the angles here. So it's a regular triangle essentially, but we use that word equilateral for it. It says to leave your answers in simplest radical form. So we're not going to be multiplying anything out yet. And they give us the length here of 8 inches. So take a look at this length. What kind of a length are we looking at here? That length is actually the radius, right? Because it goes from a vertex to the center of the triangle. So the apothem would actually be if it kind of went down and made a right angle in this direction, right? But we're not given the apothem, we're given the radius. So I'm going to sketch in my apothem, right? So we could kind of do it anywhere. I mean, if you wanted to, you could even draw that radius in here, right? An 8-inch radius here and draw the apothem down at the bottom of your triangle, but apothems can go anywhere. So I'm going to put it on this side over here. So there's my apothem. We need that, right? We need to find that length in order to use our formula. And then we also need to find the side length or perimeter. So you notice now that we've kind of created this little mini triangle within a triangle going on here. So if you remember that we have all these nice 60-degree angles because it's an equilateral triangle, right? If every angle is 60 degrees here, here, and here, if I cut that in half, then I actually have a 30-degree angle that I deal with up here. And then this is actually now a 30, 60, 90 triangle, right? So just like we had in our do now, now we can use our 30, 60, 90 formulas to go through and find missing lengths that we need. So in my 30, 60, 90 triangle here, I have a radius of 8 inches that's in my equilateral triangle, but in my 30, 60, 90, that's actually the hypotenuse or the longest side because it's directly across from my 90-degree angle. By the way, sometimes it helps students to like completely redraw this right triangle because it gets a little bit confusing saying, okay, there's little triangle and there's big triangle. So it might help to just redraw this 30, 60, 90 like off to the side and think about it there. So if I know that my hypotenuse is 8 inches, then to get to my short side, remember that the short side is just half of the hypotenuse, so I just divide it by 2 and I get 4 inches for my short side, and voila, suddenly I have my apothem. And then just like we did in our do now, to get to the long leg, we multiply by the square root of 3. So my apothem is just going to be 4, or sorry, my side length of my triangle here, this little mini triangle is going to be 4 square root of 3. So 4 square root of 3 is not even my whole triangle side length, right? It's actually just half of it because the apothem goes to the midpoint of this side over here. So if I kind of list out what I know on the side, I know that my apothem is 4 inches. I know that the side length of the big equilateral triangle is actually going to be 8 square root of 3 inches, right? Because I have to take that shorter length and multiply it by 2. So this whole side length here will be 8 square root of 3. That means that the perimeter, I'm just going to have to take 8 square root of 3 and multiply it by 3, right? 8 square root of 3, 8 square root of 3, 8 square root of 3, and there's my whole perimeter. So my perimeter, which I need for my formula, is actually 24 square root of 3. This is where students sometimes will get a little bit like, if you find an error in your homework, it usually comes back to your side lengths and your perimeter, because often students will forget to multiply this by 2 and then multiply it by 3, right? A lot of times people are just like, oh, 4 square root of 3 is a side length, let's just multiply that by 3. So just be careful that, you're kind of sketching out your shape and labeling it with everything that you know. So our whole side length is 8 square root of 3, multiply it by 3 to get the perimeter. So now we can just go through and plug it into our area formula. So my area is 1/2 apothem times perimeter. And remember, you don't have to write out this formula to show your work, but I kind of like to do it every time. So it's 1/2, my apothem is 4, perimeter is 24 square root of 3, and I just go through and simplify. So I have half of 4 is 2 times 24 square root of 3, and then 2 times 24, just those whole integer numbers, is going to be 48 square root of 3 inches squared. And remember that we're leaving it in simplest radical form, so we don't really touch that square root of 3, we just leave it alone. All right, example 2 asks us what is the area of this square, and let me put our information in here. And we're going to leave our answer again in simplest radical form. So here we're given this segment that goes from the center out to a vertex 10 inches long, so that's our radius again. So we don't really have anything that we need directly for our formula yet. So I'm going to sketch in my apothem right here, which we don't know that side length yet, or that length of the apothem yet, but we need that. And then we also are going to need the side length or the perimeter of our square, right, so that we can find out that apothem perimeter piece. So hopefully we can find out kind of the side length of this triangle right here and then use that for the square. So think about a square briefly. We have a lot of different ways that we can figure out what type of a triangle this guy is right here. What I would maybe encourage you to remember is that when I divide a square in half, if I just kind of draw like a line straight through, since these are 90-degree angles, that actually just splits our angles right here into 45-degree angles, right? So we actually do have a 45-degree angle down at the bottom there, okay? So that's to me the quickest way to explain why that guy is a 45, 45, 90 triangle, right? Because this last angle up here, by subtracting from 180 would also be 45. Other ways to do it, you could say that this length here, right, it's half of this whole side length, which means that this is an isosceles triangle, right, because half of this side length is the same as half of the bottom side length because all the sides are the same. And it's isosceles right, which means it's 45, 45, 90. You could go through and draw in all the radii and divide by 360, and you'll get these nice 90-degree angles kind of up in the center, and then divide those by 2, you get 45. So however you need to justify it to yourself, but inside the square, we do get a 45, 45, 90 triangle. So that means when we're looking at the hypotenuse here, remember that in a 45, 45, 90 triangle, we get something that looks like this. And sorry, this is a really ugly drawing again. But we have our short sides that are congruent to each other, and then the longest side is multiplied by the square root of 2. So if I want to go backwards to find out what just the leg is, that means I have to take this original side and divide by the square root of 2. And again, sorry, I'm kind of running out of space here, but that means I'm going to need to take 10 and divide it by the square root of 2. Okay, so that means then that we're going to need to do some rationalizing. So I'm going to need to multiply the top and the bottom by the square root of 2 to get rid of this square root of 2 in the bottom. Well, 10 times the square root of 2 is 10 square root of 2. Square root of 2 times itself is just going to be 2, right? Because it's the square root of 4, and the square root of 4 is 2. And then 10 divided by 2 would make 5 square root of 2. So all that kind of ugly work off to the side tells us that my short side over here is 5 square root of 2, and then also my side length down here is going to be 5 square root of 2 as well, just because it's equal, or not equilateral, but isosceles, right? The side lengths are the same. So now I can go through and list what I know. So I know my apothem is 5 square root of 2. I know my side length is 10 square root of 2, right? Because we have a 5 square root of 2, and then we have to double that for the whole side length. Don't skip that step. That's one of the most easily missed and forgotten steps in this process. So then the perimeter, if it's 10 square root of 2 for a whole side length, is going to be 40 square root of 2 because we just multiply it by 4. Now we just go through and plug everything in. You'll notice here I have 1/2 written right next to 5 square root of 2, but I actually took that half and applied it to 40, just because it's easier in my brain to do half of 40 than it is to do half of 5 and then multiply 2.5 by 40. So anyway, you should end up with the same thing either way though, where you get 5 times 20 gives me 100. And then remember the square root of 2's have to be multiplied by each other. So the square root of 2 times the square root of 2 is the square root of 4. Well, the square root of 4 is just 2. So I'm just going to say it's 100 times 2, and that gives me 200 inches squared. And that's how we find the area of the square.
All right, so our final example asks, what's the area of this regular hexagon with side length 16 inches? So let me put that 16 inches on the side length there. And we're going to round our answer to the nearest square foot on this one, which is a little bit different. So you might need to grab a calculator for this one with those square roots. So we know, right, that we're going to need the perimeter, which should be pretty easy to find because we have 16, so we'll just, multiply it by 6. But the tricky part here is going to be, how do we find this apothem that is in the middle here with not a lot of other information? So I would suggest always think about, where's your radius, where's your apothem? I'm going to sketch in one of my radii here, and we know that's going to kind of give me some kind of a triangle there. But think about, just like we did on our do now, what if I actually went in and kind of drew, I'm sorry, that's so bad, drew in the rest of my radii here? Well, we know there's 360 degrees kind of in the center of my hexagon here, all the way around. So if I split 360 into 6 different segments there, then I'm going to get a 60-degree angle kind of within each of these chunks. And with my apothem splitting that little segment in half, then half of 60 is going to be a 30-degree angle for kind of this little portion here. So if I have that 30-degree angle there, it's going to be another 30, 60, 90, right? Because I do 30 and 90, that leaves me with 60 degrees left over. So good news that we have a 30, 60, 90 triangle we can use. That's pretty awesome. That's definitely going to help us find our apothem length there. So another piece we're going to need to kind of think about is this whole length down here is 16, right? So the apothem splits that length in half. So that means that this half over here is going to be 8 feet and this half over here is going to be 8 feet. But really, we just kind of want to focus in on our 30, 60, 90 triangle here. And so I'm going to highlight this guy, right? We can kind of ignore everything else except what's going on within this 30, 60, 90 triangle. Again, if you're getting kind of like lost, because I know there's a ton of information in here, I'd recommend just redraw this triangle off to the side with all the information you know. Okay, so we have an 8-foot short leg here. So remember that if we know the short leg, that's awesome, and that helps us find the hypotenuse and the long leg. So to find the long leg on a 30, 60, 90, we're just going to multiply it by the square root of 3. So voila, I have my apothem. It is 8 times the square root of 3 feet. So now that I have my apothem, which is 8 square root of 3, I can pretty easily find my perimeter by just taking that 16-foot side length and multiplying it by 6. So my perimeter is 96, and boom, boom, there's my 2 pieces of information I need for my formula. So the area is going to be 1/2 apothem times perimeter. Plug in all your numbers. Half of 8 is 4 square root of 3 times 96. So I'm going to take 4 and 96 and multiply them together. That gets me 384 times the square root of 3, right? Because we don't want to deal with that square root of 3 until the very end. So now you might want to grab your calculator and do 384 times the square root of 3. You may need to look up directions for your specific calculator, or feel free to send me an email or a Teams message if you need help on your calculator, because they're all a little bit different. But when I plugged that in, I got 665.1075.101, blah, 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 on and on and on forever. So it's irrational number, so that's not great. But it told us to round our answer to the nearest square foot. So we can actually, fortunately, just ignore all of this extra stuff. And since there's just a 1 right here, that means I'm just going to cut everything off and just kind of leave it at 665. So my final answer is going to just be 665 feet squared, and that's the area of the hexagon. So here's your assignment. Please log on to Teams or log on to your textbook and get this done, and I will see you guys later this week.